formal charge is actually the charge assigned to an atom in the molecule, assuming all the bonding electrons are equally shared, even if there is an electronegativity difference between the atoms that are actually bonded. So there is actually a formula that calculates the formal charge. The formal charge is the valence electrons minus the lone pair of electrons. The lone pair of electrons are also called the non-bonding electrons, plus the shared electrons, and the shared electrons are also called the bonding electrons. So you may see those terminology being used in some books. So lone pair electrons are the non-bonding electrons. Okay, so let me take an example. If I have OH and I want to try to figure out what the formal charge on this oxygen is in this particular case, that's going to be 6. So 6 is going to be the valence electrons in the oxygen minus, now figure out how many lone pair electrons you got, or the non-bonding electrons you have on the oxygen, and looks like I have 3 lone pairs, and that brings in 6 electrons, because remember, one lone pair has 2 electrons in there, so 6, and then plus 1 bond there, so there's a bond between the oxygen and the hydrogen, and then keep in mind if there isn't a bond between oxygen and the hydrogen, then that one bond brings in 2 electrons. So one bond is going to be 2 electrons, so 2, and then shared electrons, or the bonding electrons, will be divided by 2. So 2 divided by 2, and that gives you a formal charge of -1. So that's actually going to be the oxygen with the formal charge of -1. So I can go ahead and write that down here. And if you guys recall, what's an OH minus? Well, the OH minus is one of the polyatomic anions that you had to memorize. It's the hydroxide. Okay. Now let me take another example. What if I have carbon dioxide? The Lewis-Dot structure for the carbon dioxide looks like this. You got carbon double bonds with the oxygens, and each of those oxygens has 2 lone pairs. And I can go ahead and calculate the formal charge on each of those. Let's figure out the formal charge on the carbon first. How many valence electron carbon has? 4. Minus, okay, how many lone pair electrons you got on the carbon? So right now, carbon do not have any lone pairs on it, so that means that's just going to be 0. And then plus, how many bonding electrons we got, or how many shared electrons we got. So remember, there isn't a double bond between the carbon and the oxygen, and each double bond is made of 4 electrons. So think of this way: one bond constitutes 2 electrons. So if you have a double bond, that constitutes 4 electrons. So now you have 2 double bonds that brings in a total of 8 electrons. So it's going to be 8 divided by 2. So that comes out to be 0. Okay, so it seems like we got a 0 formal charge on the carbon here. And I can go ahead and calculate the formal charge on the oxygen as well. And let's do that right here. And each of those oxygens are actually in the very similar condition. So whether you calculate the formal charge on the right oxygen or on the left oxygen, it would be the same, because both oxygens has 2 lone pairs and 1 double bond. So in this particular case, you got 6 valence electrons for the oxygen, and if the valence electrons, remember, is just going to be the group number in the periodic table, minus how many lone pair electrons we got on the oxygen? 1, 2, 3, 4. We have 2 lone pairs, that brings in 4 electrons. So 4, and then plus how many bonding electrons? Well, each oxygen has a double bond. That means that brings in 4 electrons, or 4 shared electrons. So it's going to be 4 divided by 2. And that comes out to be 0. Okay, so then oxygen has a formal charge of 0 here, and carbon has a formal charge of 0 as well. Okay, let me take another example. What if I have NH4 plus, or NH4? Well, there's a plus charge on the NH4, but if I go ahead and draw that out, this is how the Lewis-Dot structure of NH4 is. Okay, and let's try to figure out the formal charge on this nitrogen right now. So how many valence electron nitrogen has? So you may want to pause a little bit here and figure out the formal charge on its own and then match if it comes out to be correctly. So the number of valence electron on the nitrogen is going to be 5 minus, do we have any lone pairs on the nitrogen? And turns out there's no lone pair on the nitrogen, so it's going to be 0. I don't see any electrons on the nitrogen, so that's 0. And then plus, how many bonding electrons we got? There are 4 single bonds around the nitrogen, so that means that's going to be a total of 8 electrons, so 8 divided by 2, and that will give you a positive 1 formal charge. So when you see this polyatomic cation that you had to memorize, NH41+, which is also called the ammonium ion, it has a 1 plus formal charge, but we never really worried about where that 1 plus is coming from. The 1 plus actually is coming from the nitrogen having the 1 plus formal charge. So that's how you actually calculate the formal charges on the atoms in a molecule. Okay, well, it's usually a good idea to know the formal charges of some of the most commonly used atoms. And it's gonna help you a long way in Gen Chem, and most importantly, it's gonna help you a long way when you take organic. Let's focus on carbon. If carbon has 4 bonds, okay, so that could be 4 single bonds, or 1 triple bond, or 2 double bonds. Okay, as long as it makes a total of 4 bonds with no lone pairs, then the formal charge is going to be 0. However, if carbon has only 3 bonds and there is 1 lone pair, then it's going to have a formal charge of -1. Now, like I said, you don't necessarily have to memorize in too much details. You can always calculate the formal charge, but these are some of the atoms that's going to be being shown up most commonly, especially in organic chemistry. So you want to make sure you have a general idea of the formal charges of these atoms. If carbon still have 3 bonds, no lone pair, then it's going to have a formal charge of +1. It usually has a positive charge at that point. Okay, as far as the nitrogen go, nitrogen likes to have 3 bonds. Now, the breakdown of the 3 bonds could be just 1 triple bond, or 1 double bond, 1 single bond, or 3 single bonds. As long as it makes a total of 3 bonds, that's all that really matters. And it usually likes to have 1 lone pair. So whenever it's in that scenario, it's going to be a 0 formal charge. And I can take an example of ammonia, NH3. And when you draw the Lewis-Strauss structure, it's going to have a lone pair on the nitrogen. It's going to, I'll just go ahead and write down the lone pair there. If nitrogen has 4 bonds with 0 lone pair, then it's going to have a +1 formal charge. And we actually did that example right there. Nitrogen had 4 bonds in ammonium, and it came out to have a formal charge of +1. So that's also very common. If nitrogen has 2 bonds, and there is actually 2 lone pairs in that case, then the formal charge is going to be -1. And a good example is going to be NH2 with 2 lone pairs on the nitrogen in that case. So most commonly that's you guys going to be seeing. For the carbon, you can see all 3 possibilities. You must have 4 bonds in order to have a 0 formal charge, but you could see 3 bonds with 1 lone pair or the 0 lone pair, and they would have a different formal charges. For the nitrogen, you would see 3 bonds. This one is very common. 4 bonds is also very common. This 2 bonds, you will see that in organic chemistry. Let's talk about oxygen. Oxygen likes to have 2 bonds. Okay, so let's change that here. Oxygen likes to have 2 bonds with 2 lone pairs, and anytime you see that, it's going to have a formal charge of 0. And a very good example is water, actually. In water, when you draw the Lewis-Strauss structure, oxygen has 2 lone pairs and then 2 bonds, so that will have a formal charge of 0. The oxygen could have 3 bonds and 1 lone pair, and if that's the scenario, it's going to have a +1 formal charge. And a really good example is the hydronium ion, H3O+. It's got one lone pair on the oxygen and the three bonds around. So that positive in that molecule is coming from the oxygen in that case. And then oxygen could have one bond where it will have three lone pairs and the formal charge would be -1. And a really good example is the hydroxide ion, and we just did that example earlier when we were trying to calculate the formal charge. Okay, as far as the hydrogen go, hydrogen likes to have one bond, no lone pairs, and it will have a formal charge of 0. Okay, so that's the most common way of you will be seeing in the chemical bond, um, in the chemical molecule when you see the hydrogen. If you see a molecule, if you see a hydrogen by itself, then whatever the charge on the hydrogen gonna be, that would be the formal charge. For example, I can write down, okay, I can write down H, maybe I can just do it right down here. If I write CH plus, that means the formal charge at this point on the hydrogen is +1. Okay, if I see H1 minus, then the formal charge on the hydrogen at this point is -1. Okay, so those are the most commonly used elements in GenChem. You would see other elements like sulfur, phosphorus. They don't really have a specific way of getting a formal charge of 0. They have multiple ways of getting a formal charge of 0. So at that point, you want to make sure you use the formula to calculate the formal charge. Okay, well, let's talk about drawing the Lewis-Strauss structure and then drawing the resonance. And I'll take an example. I'll probably take a couple of examples. But let me start out with this example. It's an OCN1 minus. Okay, so if you guys recall, the first step is going to be the total valence electrons. And the total valence electrons in this particular case, I have oxygen. Oxygen is going to have 6 valence electrons, plus carbon is going to have 4, nitrogen is going to have 5, and then 1 minus means there's going to be an extra electron in there, so make sure you go ahead and add that out. So this is going to come, this will come out to be a 16 total valence electrons. You must use all 16 valence electrons in this particular case. The next step in drawing the Lewis-Strauss structures, remember, is picking the central atom. All right, so your central atom is going to be the carbon in this case, and I'll put down the carbon at the center, and then I'll have nitrogen and the oxygens as the surrounding as far away from one another. So when you do that, the next step will be placing one bond or an electron pair between the central atom and the surrounding atom. So I'll go ahead and put down one bond between the carbon and nitrogen and one bond between the oxygen and the carbon. Okay, so when you do so, how many electrons did you use? Well, that turns out to be 4 electrons used. So when you subtract 4 electrons from 16, you still have 12 more electrons to go. And what we have learned after that is figure out or fulfill the octets of the surrounding atoms first. Okay, so what I can do, I can go ahead and fulfill the octets of the surrounding atoms by placing 6 electrons on each of those surrounding atoms momentarily. Now that uses up all the 12 electrons and, a matter of fact, all the 16 valence electrons we got. Now before you finalize your structure, you got to make sure you have your octets completed. So for example, let me just copy this down and move this a little bit up here. Okay, so for example, if I can look at the octets, nitrogen is happy, it's got 8 electrons. Oxygen is happy, it's got 8 electrons. Each of them has 3 lone pairs and 1 bonding pair, so that totals to be an 8 electrons. When you look at the carbon, it doesn't really have 8 electrons. It's got only 4 electrons so far because it's got only 2 bonds, or 2 single bonds in this case. So to draw a valid Lewis-Strauss structure, you must complete the octet of the carbon as well. So to do that, there's a couple of things you can do, and I'll probably show that with different colors. I can have the lone pair from the oxygen, one lone pair from the oxygen, and one lone pair from the nitrogen coming in and creating a double bond around the carbon. So then your loose star structure will look like this. So I'll have carbon, double bond, and nitrogen, and then oxygen. So you have two lone pairs on the oxygen, two lone pairs on the nitrogen. All right, so that's one possibility. Okay, then it's all about kind of getting all the possibilities of drawing the loose star structures. Uh, then your next possibility would be, how about getting maybe two lone pairs from the oxygen into to create a triple bond between the carbon and oxygen. It may not be the best structure, but it's just one of the possibilities. All right, so have this lone pair going in there and have one of the other lone pairs going in there as well to create the triple bond. So I'll have carbon still a single bond with the nitrogen, so leave that as it is, but now you have a triple bond with the oxygen, so then this structure looks like this. That's your second possibility. Your third possibility would be, what if I want to actually use, let's change the color there. What if I want to actually use two lone pairs from the nitrogens to create the triple bond, and then see how that structure looks like. So this is going to be carbon triple bond, the nitrogen, and then the oxygen will still have the single bond, just like this. Make sure you show all the remaining non-bonding or the lone pair of electrons there. Okay, so whenever you can draw multiple resonance structures, there is always a chance that one of them is going to be the most stable or the most contributor to the resonance structures. You know, that's not always the case, but a lot of time you can pick one to be the most stable. Now, in order to actually do that, the first thing you need to do is calculate the formal charges on every single atom in every single resonance structure. So let's go back to the first resonance structure and try to calculate the formal charge on this oxygen here. Now I'm going to do one example, and the rest of them you guys should do it. So then this oxygen right here, the formal charge is going to be 6 valence electrons minus, I got 4 electrons coming from lone pairs, and then plus 4 bonding electrons, so 4 divided by 2, that's going to give you a 0 here. Okay, so remember what we have said earlier, if oxygen makes 2 bonds and 2 lone pairs, it will have a formal charge of 0. Okay, so that's going to be 0. Okay, let's look at the carbon there. So draw down there. Carbon has 4 valence electrons minus how many lone pair electrons on carbon? None. There's no lone pair on the carbon, so 0 plus how many bonding electrons on carbon now? Well, there's 4 bonds around carbon, so that means that's going to give you a total of 8 electrons. So 8 divided by 2, that will give you 0 as well. So that's going to be a 0 formal charge here. Now we can look at our nitrogen as well. So their nitrogen's formal charge is going to be, I have 5 valence electrons minus, I have 2 lone pairs of electrons on the nitrogen, so that's going to be 4 electrons, plus how many bonding electrons? You got 2 bonds, so that's going to be 4 divided by 2. And when you do this math, it's going to come out to be a minus a 1 formal charge. Okay, so right now, this particular nitrogen actually have a minus 1 formal charge. Okay, so one of the things you always want to keep in mind that the sum of formal charges of the atoms in the molecule must equal to the overall charge of the molecule. So if you go back, the overall charge in this particular ion is 1 minus. So far right now, nitrogen is the only one in this first resonance having 1 minus formal charge. So that does give you an overall of 1 minus charge in the molecule. Okay, so that's your one resonance. That's a formal charge on one of them. So make sure you calculate the formal charge on all of them. So you may want to pause the session and calculate the formal charges on all of them. But once you calculate those out, I'm going to go ahead and just write it out. So oxygen in the second green resonance structure here, oxygen having 3 bonds and 1 lone pair, so that means it's going to have a positive 1 formal charge. Carbon having 4 bonds around, so 1 triple bond, 1 single bond, so it's still going to have a 0 formal charge. When you look at nitrogen, well, right now, nitrogen actually, even in kind of a little bit worse scenario, you got 3 lone pairs around, and one bonding domain. So that's going to give you a formal charge of -2. So make sure you go ahead and use the formula and calculate that out. Now, even though you have multiple atoms with the formal charges, nitrogen having -2, oxygen having +1, your overall charge in the molecule is still -1, and that's what we really need to have. You cannot change the overall charge of the molecules. If you do that, then it's going to be an invalid resonance structure. Okay, well, let's look at the third one now. Oxygen's having 3 lone pairs and 1 bond, so go ahead and do calculate the formal charge on this third oxygen here. And if you go back and look at the chart that I had made earlier, whenever oxygen has 1 bond with 3 lone pairs, it will have a formal charge of a -1. Carbon is still in very similar condition. We got 4 bonds around carbon, so that's going to be a 0 formal charge. Nitrogen having 1 lone pair, 3 bonds, it's going to have a 0 formal charge. So overall, it's still going to have a -1 formal charge, and that's what we really need to have. Okay, so those are the 3 possible resonance structures you got in there. Now, the question is, how would you determine the most stable resonance structure? Okay, so then when we look at, and the criteria is like this. You got the first thing you look for, the atoms must, in the resonance structures, must have the octet completed. So every single atom should have the octet completed. Obviously, if there isn't a violation in the octet, then it's a different story. For example, if you have a hydrogen being involved in the structure, hydrogen doesn't need more than 2 electrons. So those are the things you want to keep in mind. But when I look at every single of those atoms in there, the oxygen in the first resonance, carbon, and the nitrogen, they all have 8 electrons around them, so they all have the octet completed. So that's the very first thing you always want to look for. And that's the reason this original structure that we have actually created wasn't a good resonance structure, because carbon did not have an octet completed here. Carbon did not have the octet completed there. Okay, so if that doesn't differentiate, you move on to the second one. The best resonance structure is going to have the least number of atoms with any formal charge, whether it's positive or negative, but you want to make sure you have the least number of atoms in the resonance structure with the formal charge. Well, let's look at one by one. Look at the first resonance structure. Let's call that A. In A, you have only nitrogen with a -1. Okay, so far we good. Okay, in second resonance structure, called that B, we got oxygen with a +1 resonance charge, a formal charge, and the nitrogen with a -2 formal charge. So, all right, we got 2 elements, 2 atoms with the formal charges. Okay, so that seems like it's going to be a bad resonance structure. Then the third one, in this case, we still have only 1 atom with the formal charge. So at least it doesn't help you to determine the best resonance structure, but it does tell you who is going to be the worst resonance structure. It's going to be the B. So B resonance is going to be the worst resonance structure in this particular case. All right. So then the next step is going to be the resonance structure. If you like, now we have A and C with the same number of elements having the same type of formal charge. So then the next thing you want to look for is whoever is actually the most electronegative is going to be, it should have the negative formal charge. Okay, so now when I look at A, in A I have nitrogen with a -1 formal charge, and when I look at C, I got oxygen with a -1 formal charge. So that's the only difference between those two resonance structures I got. So now I got to go back in the periodic table and check out of oxygen and nitrogen who is more electronegative. All right, so that's a question for you guys. Who is more electronegative in this case? Well, your oxygen is going to be more electronegative than the nitrogen. So if oxygen is more electronegative, it wants to have that extra electron pair more than the nitrogen. And that's the reason the C would be the most stable or the most contributor of the resonance structure. So I can go back and be like, okay, my C resonance structure is going to be the most stable, and then your B is going to be the least stable. Okay, so this is how you're going to be determining the most stable and the least stable resonance structures in among various resonance structures. So I'll have some more examples posted in a separate video. Hopefully it was helpful,